Good morning, everyone. Myself, Bharat. Today, I am here to present my tech talk presentation. Today, my topic is Bayesian linear regression, learning distribution over parameters instead of point estimates. Introduction: Bayesian linear regression model parameters uncertainty to returning full Poisson distributions rather than point estimation. The enables principles underestimate qualification and improve decision making under risk. Bayesian versus frequentist parameter distributions. Bayesian interferes yield of Poisson distribution over coefficient capturing parameters variability. Use the Poisson mean and median for prediction and full distribution for uncertainty aware decisions. Uncertainty qualifications. Predictive outputs includes credible intervals that reflect both parameters and noise uncertainty. These intervals support risk aware planning and model reliability assessment. Prior influence. Prior encodes domain knowledge for regularize estimates. Choose informative pairs when data are scarce. Access sensitivity by comparing posture under alternative pair significations. Model specifications. Likelihood choice. Specify a livelihood responsible. Gaussian for continuous outcomes. Correct likelihood choice ensures valid probability, uncertainty, and integrity in force. Select priors for coefficient and noise variance to reflect belief sign enforcement regularities. Common choices Gaussian priors for coefficient and inverse gamma or half Cauchy for variance. Hyperparameter setup. Choose hyperparameter for prior and noise models to reflect domain knowledge and desired regularization. Perform grids research search and impulse bands to tune them and validate impact via sensitivity analysis. Interference methods. Analytical postures. And conjugacy holds drive a closure from postures distributions from parameters. Gaussian prior with Gaussian likelihood. This yields exact solutions for means time convergences for fast interference. Conjugate prayers. Select conjugate prayers to simplify computation Gaussian for coefficient inverse gamma for variance. Conjugacy yield trackable update and interpretable posterior prayers and hyperparameters. Approximate interference. Conjugate prayers. Select conjugate prayers to simplify computation. Gaussian for coefficient inverse gamma for variance. Conjugacy yield trackable updates and interpretable posterior hyperparameters. Approximate interference. Use MCMC or variation interference when analytical priors are unavailable. MCMC provides asymptotical exact simples. Sixth offer faster approximates priors for stability. Prediction and evaluation. Posterior predictive. Compute the posterior predictive distribution for forecast of new outcomes integrating parameters uncertainty. Report predictive intervals alongside points forecasting for decision making. Uncertainty propagation. Propagation parameters uncertainty through predictions to qualify outcomes, variability, and tail risk. Use predictive samples to estimate expected losses to risk measures under uncertainty. Model comparison. Compare model via predictive performance, log predictive density, and information critical loss wide and low. Favor models with better calibration, uncertainty, and predictive accuracy. Likelihood choice. Specific a likelihood for the responsible example Gaussian for continuous outcomes. Correct likelihood choice ensures valid posture uncertainty and interpretable interference. Prior selection. Selection prior for coefficient and noise variance to reflect benefits of or enforce regulation. Common choices. Gaussian prior for coefficient and inverse gamma or half Cauchy for variance. Hyperparameter setup. Choose hyperparameters for priors and noise models to reflect domain knowledge and desired regularization. Perform grid search or empirical Bayesian to tune them and validate impact via sensitivity analysis. Interference methods. Analytical postures. When conjugate holds diverse a loop from Poisson's distribution from parameters. Example Gaussian priors with Gaussian likelihood. This yields exact solution for means and converses for Foch interference. Conjugate prayers. Select conjugate prayers to simplify communication. Gaussian for coefficient, inverse gamma for variance. Conjugate yields trackable, update, and interpretable prior hyperparameters. Approximate interference. Use MCMC or variable interference when analytical procedures are unavailable. MCMC provides asymptotical example samples. Sixth, offer faster approximate procedures for scalability, prediction, and evaluation. Analytical procedures. In conjugacy holds derive a closure from Prior distribution from parameters. Example Gaussian priors with Gaussian likelihood. This yields exact solution for means of covariations and fast interference. Conjugate priors. Select conjugate priors to simplify compilation Gaussian for coefficient inverse gamma for variance. Conjugacy field trackable upgrades and interference with pressure hyperparameters. Approximate interference. Use MCMC variation interference with analytical postures and unavailable. MCMC provides asymptotical example 6 offer fast approximates postures for scalability, prediction and evaluation. Posture predictive. Compute the posture predictive distribution for to fasten new outcomes integration parameters uncertainty. Report predictive intervals alongside point forecasting for decision making. Uncertainty propagation. Propagate parameters uncertainty through prediction to qualify outcomes, variability, and tail risk. Use predictive samples to estimate expected loss or risk measures under uncertainty. Model comparison. Compare model where predictive performances log predictive density and information criteria like WIC and low favor model with better calibration uncertainty with predictive accuracy. Conclusion: Bayesian linear regression provides principal uncertainty qualification by model parameter distribution. Choose prior and interval methods to balance interpretability, computational cost, and predictive reliability.